Well, hello and welcome again to our journey into algebra and number theory. And this section is called the structure of Zm and Um. It's probably the most technical and perhaps the hardest of the sections I'm going to record in this little series. But it will introduce you to some very important ideas, both from algebra and group theory, and also some very interesting ideas from number theory. And by studying the group theory, we're then able to answer interesting questions about the number theory in using group theoretic ideas rather than the classical proofs that you may see elsewhere. So first concept is this idea of isomorphism of groups. And if you haven't come across these before, let me just briefly explain what these are about. So a very simple example, suppose I've got a collection of 12 tests. And I could label them test 1 up to test 12, or I could take each of the tests and relabel them as test A up to test L. And the name we give them doesn't alter the contents of each test. They're the same test, I've just given them different names. Well, that's a very trivial example of this idea of isomorphism. So suppose I'm going to take these two groups U8 and U12. So U8 are the numbers that are relatively prime to 8, 1, 3, 5, 7, and U12 are the numbers that are relatively prime to 12, 1, 5, 7, 11, and I've drawn up their multiplication tables. And if you look carefully at these, you can see that the multiplication tables are essentially identical to each other. They've both got 1s along the main diagonal, and the structures look very similar. For example, this number here is the same as this one, this number here is the same as this one, and so on. And so, in other words, these two multiplication tables are identical if I just relabel the elements as follows. So I'm going to relabel, I'm going to leave 1 alone, so 1 gets mapped to 1. I'm going to relabel this 3 as the 5 over here. I'm going to relabel this 5 over here as the 7 here, and I'm going to relabel this 7 as this 11 here. So this sets up, in fact, a one-to-one correspondence between the elements of these two groups, which preserves the structure, that is, the multiplication tables. If I did this change of relabeling on here, I would get exactly this one here. So the structure is preserved under this one-to-one correspondence. And we're going to say then that these two groups are isomorphic to each other. It's simply a Greek word meaning having the same shape or the same form. So, as I've written here in the notes, in other words, the structure of the two groups is identical. The only difference between the two groups are the names of the elements. And as I said, we say these two groups are isomorphic, and that's the notation we're going to use. It's an equal sign with a little squiggle up the top. We read this as U8 is isomorphic to U12. This concept of isomorphism is absolutely fundamental in group theory because you want to be able to see how many different groups there are of a given order, up to isomorphism, that is, up to relabeling. Well, second example, I'm going to take the multiplication table for Z5 under multiplication. So there's the multiplication table. And now, if you try and relabel any way you like, if you try to relabel these elements here to turn them into the elements of the groups U8 or U12 that we saw above, well, you just can't do it. It doesn't work properly. So the elements can't be relabeled to give U8 or U12, and that tells me that this Z5 under multiplication is not isomorphic to U8. On the other hand, if I take the group Z4 under addition, then its addition table looks like this. Here is the addition table. And if you compare these two, the multiplication table with Z5 and the addition table for Z4, then you do see that you can relabel one to the other, and here's the relabeling. You map 0 to 1, 1 goes to 2, 2 goes to 4, 3 goes to 3 across these two tables here. And that's going to tell us then that the group Z4 under addition is isomorphic to the group Z5 under multiplication. So you don't even need to have the same operation going on here. You can have two groups with different operations that could be isomorphic to each other. So this, as I said, gives an isomorphism between Z4 under addition and Z5 under multiplication. So we feel a definition coming on. So we've got, I take two groups, G under some operation star, and a group H under some operation called dot here. If these are groups, then G is said to be isomorphic to H, and we write G with this symbol is isomorphic to H if and only if there's a one-to-one correspondence, that is a bijection, F between G and H, such that the structure is preserved. That is, if I multiply two elements in G using that multiplication, then I apply this one-to-one correspondence, this map F, then I get the same as if I were to apply F to each of the elements G1 and G2. That would then land me in H, and then I combine those two elements using the multiplication in capital H. So this last condition says that F preserves the structure from one group to the next, i.e. it's simply a relabeling and it preserves structure. And this F is called an isomorphism between the two groups. Now, what does that? Let's have a look at cyclic groups, and we'll see that for a given size, there's only one cyclic group of given order. So recall that we use this notation, angled brackets around A, where A to the n was 1, for some positive integer n, and we called this set that we get from all the powers of A to be a cyclic group of order n, and we wrote C sub n was 1a squared up to a to the n minus 1. And this was a group of order n. We notice also that the group Zn under addition, modulo n, is isomorphic to this group. Under the isomorphism, what do? You map 0 in here to the 1 in Cn, you map 1 in here to A, you map 2 in here to A squared, and so on, and there's the obvious one-to-one correspondence. Simply you could write f of k as A to the k. This is clearly a one-to-one correspondence. It's one-to-one and onto, and it preserves the structure between the two sets. So that tells me then that these two groups, Cn, the abstract cyclic group, is isomorphic to the additive group of integers modulo n. Now, lovely theorem, if P is prime, primes are always so interesting, if P is prime, then any group of order P is isomorphic to Zp under addition. So in other words, there is only essentially, for each prime, there is essentially only one group of order P. And the proof of this is worth just going through. It's very simple, but just to show you how this works in proof context. So we take G to be a group of order P, P is prime. We take A to be any element of G, but not one, not the identity in the group. Now, since the order of A divides the order of G, and this G has order P, well, the order of A is either 1 or P. It can't be 1 because we said A wasn't the identity, and that means the order of A is P, and that means then this G then is simply the thing you get by taking all the powers of A, and A to the P is going to be the unit element in the group. So that tells me that any group of prime power is can be written as a cyclic group. And now we take our isomorphism, G into Zp, and it's exactly the one we did before. we map 1, that's the identity in the group G, gets mapped to 0, A gets mapped to 1, A squared to 2, and so on. And that is clearly an isomorphism, and so this group G, this abstract group G of order P, is just isomorphic to the integers modulo P under addition. So that's lovely, because that tells us the structure of Zn under addition then is very simple. It's always cyclic. It's always cyclic. Now the group UN, however, is not always cyclic, and it is more complicated, as we'll see. We have a look at some examples just to try and get some feel for what's going on. So U sub 7 are the numbers, the integers mod 7 that are relatively prime to 7, so that's 1 up to 6 because 7 is prime. Now I'm going to pick one of the elements. I'll pick 3 and I'll take all the powers of 3. So 3 squared is 9. 9 times 3 is 6 modulo 7. 6 3s are 4 mod 7. 4 3s are 5, and so on. So I take the generator of 3, I get this thing here, which is a subgroup. And in fact, if you look at it, it is exactly the group U7 that we started with. Now that tells me that U7 then is cyclic. And there's the generator for it. It may have other generators, but I've just found that 3 is a generator, so this group is cyclic. On the other hand, U10, which consists of the numbers relatively prime to 10, this also turns out to be generated by 3. So if you take 3 squared is 9, 3 cubed is 7, 3 to the 4th is 1, and that's just the elements of U10. So that's also cyclic. So you might have guessed initially that when you see U7 is cyclic, you might have thought, well, if this number's prime, it's cyclic. But, well, 10 is not prime, but this group also turns out to be cyclic. On the other hand, U12, which is just 1, 5, 7, 11, this is not cyclic because every element here has order 2. So as soon as you take the square of anything here, you just get back to 1, so you won't get a generator here. So we're going to investigate then what values of n make this U sub n into a cyclic group. So to achieve this, again, we need to understand a little bit more group theory, and in particular, we're going to take this UN group and we're going to try and decompose it into smaller groups. And I'll start that in the next video.